George Cantor was born in St. Petersburg, Russia, in 1845. The city, known for its rich cultural and intellectual heritage, provided a stimulating environment for young George. His family was devoutly religious and instilled in him a strong sense of faith. This religious upbringing was a cornerstone of his early life, shaping his worldview and moral compass. This faith would later influence his mathematical thinking, intertwining his spiritual beliefs with his pursuit of knowledge. Cantor often found himself contemplating the infinite, a concept deeply rooted in both theology and mathematics. Cantor's father recognized his son's intellectual gifts early on. He saw in George a prodigious talent that needed nurturing and guidance. He encouraged young George to pursue a career in engineering, believing it to be a stable and respectable profession. Engineering was seen as a practical application of mathematical principles, and his father hoped it would provide a secure future. Despite his father's wishes, Cantor felt a strong pull towards mathematics. The abstract beauty of numbers and theorems captivated him in a way that engineering never could. He excelled in his studies, particularly in mathematics and physics. His teachers were often amazed by his ability to grasp complex concepts with ease and his insatiable curiosity. He completed his secondary education in Germany and then enrolled at the University of Berlin. The university was a hub of intellectual activity, attracting some of the brightest minds of the time. At Berlin, he studied under renowned mathematicians like Karl Weierstrass, Ernst Kummer, and Leopold Kronecker. These mentors played a crucial role in shaping his academic journey, providing him with the tools and inspiration to explore new mathematical frontiers. Little did he know, this education would lay the foundation for his groundbreaking work in set theory. Cantor's time at the University of Berlin was not just about absorbing knowledge. It was about challenging existing paradigms and pushing the boundaries of what was known. His interactions with these great minds ignited a passion for discovery that would drive him throughout his career. Cantor's initial research focused on number theory, a traditional and well-established field in mathematics. He quickly demonstrated his talent and published several well-received papers. However, his interests soon began to shift towards a more abstract and unconventional area, the study of infinite sets. This shift was inspired by his study of the work of Georg Riemann. Riemann's ideas about the nature of infinity sparked Cantor's imagination. He began to develop his own theories about infinite sets, challenging the prevailing mathematical dogma of the time. This marked the beginning of his journey into the uncharted territory of set theory. Cantor's revolutionary idea was to treat infinity not as a vague concept, but as a mathematical object. He developed the concept of a set, a collection of distinct objects, as the foundation of his theory. This seemingly simple idea had profound implications. Cantor defined different types of infinity. He introduced the concept of cardinality, a way to measure the size of infinite sets. He demonstrated that there are different sizes of infinity, a concept that had never been considered before. His work challenged the foundations of mathematics and opened up new avenues of exploration. One of Cantor's most groundbreaking discoveries was the concept of countable and uncountable infinities. This was a revolutionary idea that changed the landscape of mathematics forever. He proved that the set of natural numbers, 1, 2, 3, and so on, is countable, meaning its elements can be put into a one-to-one correspondence with the natural numbers themselves. This was a significant step in understanding the nature of infinity, as it provided a way to categorize and compare different infinite sets. However, he also showed that the set of real numbers, all numbers on the number line, is uncountable. This was a more complex and profound discovery, as it revealed that not all infinities are created equal. This means that no matter how you try, you cannot list all the real numbers in a sequence. The real numbers are so numerous that they cannot be matched one-to-one with the natural numbers, highlighting a deeper level of infinity. This discovery revolutionized our understanding of infinity. It opened up new avenues of thought and research, leading to further advancements in set theory and beyond. It demonstrated that there are different magnitudes of infinity, a concept previously unimaginable. Cantor's work laid the foundation for modern mathematical analysis and has had a lasting impact on various fields, including computer science, physics, and philosophy. His insights into the nature of infinity continue to inspire and challenge mathematicians to this day. Section 5. The resistance Cantor's battles with mathematical orthodoxy. Cantor's revolutionary ideas were met with resistance and even hostility from some of the most prominent mathematicians of his time. His former professor, Leopold Kronecker, became his fiercest critic. Kronecker believed that mathematical objects should be constructible, meaning they should be definable by a finite number of steps. Cantor's concept of uncountable infinities directly challenged this view. Kronecker used his considerable influence to block Cantor's publications and appointments, hindering his career advancement. Cantor's work was also attacked by other mathematicians who found his ideas too radical and unsettling. Section 6. Shadows of Genius. Cantor's personal struggles. The constant opposition and criticism took a toll on Cantor's mental health. He suffered from bouts of depression throughout his life. The lack of acceptance for his work, combined with his personal struggles, led him to be admitted to a sanatorium several times. Despite these challenges, Cantor continued to defend his theories with unwavering conviction. He believed that his work was not only mathematically sound, but also had profound philosophical and theological implications. He saw his exploration of infinity as a way to understand the infinite nature of God. Section 7. A lasting impact. Set theory's influence on mathematics. Despite the initial resistance, Cantor's work gradually gained acceptance within the mathematical community. His ideas proved to be incredibly fertile ground for further research. Set theory became a fundamental language of mathematics, providing a framework for understanding and expressing mathematical concepts across different fields. Cantor's work laid the foundation for modern mathematics and had a profound impact on areas such as topology, analysis, logic, and computer science. His concept of cardinality revolutionized our understanding of infinity and opened up new areas of mathematical exploration. Section 8. Beyond Infinity. Cantor's enduring legacy. George Cantor died in a sanatorium in 1918. However, his legacy continues to inspire and challenge mathematicians today. His work on set theory is now considered a cornerstone of modern mathematics. It is taught in universities around the world. Cantor's ideas continue to spark new discoveries and push the boundaries of mathematical understanding. His story reminds us that even the most revolutionary ideas often face resistance. Yet truth and innovation have a way of prevailing in the end. Section 9. The father of set theory. Honoring a mathematical visionary. George Cantor's journey was marked by both intellectual triumph and personal struggle. Born in 1845 in St. Petersburg, Russia, Cantor showed an early aptitude for mathematics. His family moved to Germany when he was a child, and it was there that his mathematical talents truly began to flourish. He dared to explore the infinite, challenging the established mathematical norms of his time. Cantor's revolutionary ideas about infinity and set theory were initially met with skepticism and resistance from his contemporaries. Many mathematicians of the 19th century found his concepts difficult to accept, as they defied the traditional views of mathematics. His unwavering belief in his work, despite facing fierce opposition and personal hardship, is a testament to his genius and his unwavering pursuit of mathematical truth. Cantor's personal life was also fraught with challenges. He suffered from bouts of depression, which were exacerbated by the professional isolation he experienced due to the controversial nature of his work. Today, Cantor is rightfully recognized as the father of set theory. His groundbreaking work laid the foundation for much of modern mathematics, influencing fields as diverse as topology, logic, and computer science. Cantor's theory of transfinite numbers and his development of the concept of cardinality have become fundamental components of mathematical education and research. His work continues to shape our understanding of mathematics and the infinite. Cantor's ideas have opened up new avenues of thought and have inspired countless mathematicians to explore the mysteries of the infinite. His contributions have not only advanced mathematical theory, but have also had a profound impact on the philosophy of mathematics. His legacy serves as an inspiration to mathematicians and thinkers around the world, reminding us that even in the face of adversity, the pursuit of knowledge and the exploration of the unknown are endeavors worthy of our greatest efforts. Cantor's life and work exemplify the courage and determination required to push the boundaries of human understanding. His story is a powerful reminder that true innovation often comes from those who are willing to challenge the status quo and persevere despite the obstacles. As we honor George Cantor, we celebrate not only his mathematical achievements, but also his enduring spirit of inquiry and his profound impact on the world of mathematics.